Hello! In the last section, we got familiar with graphs, just in general, kind of them giving us a graph and us kind of interpreting what we're given, and then we plotted a few points just to get the hang of it. So now we're going to kind of put those together. We're going to use points to help us graph lines. And then in this section is just kind of an intro to that. We'll only have one method on how to do it in this section, but in the next sections to come, we'll see that there are alternate ways to do it that you might prefer, which makes it easier, or you might not like it as much and you want to stick with the first way. There are a lot of ways to graph a line, as we'll see. Okay, so let's see, the very kind of beginning, just to get the hang of it. The idea here is, remember in chapter 2, we learned how to solve all kinds of equations. We had all these steps. This is how you solve for x. If you have fractions, you can get rid of them. If you have decimals, you can get rid of them. You know, we kind of mastered those types of equations. And notice that those equations that we solved, they only had one variable. So now what we'd like to do is we're interested in making it a little more complicated. So you see this equation here that I'm boxing, 3x minus 2y equals negative 6. Now we have an equation with two variables. So it won't be possible to solve it like we're used to. I can't really just, for example, isolate x and figure out what x is, because I don't know what y is. So we'll have to kind of come up with a different method on how to solve it. And in fact, let me see, just down here in the next kind of paragraph here, it says, equations in two variables, like the one that's in the box, they have solutions that are ordered pairs, so it looks like x comma y. And that's because since there are two variables, in order to talk about a solution, you'd have to talk about both coordinates, what's x and what's y. So, and also, in fact, every equation of this form has an infinite number of solutions. And we're not used to that, I guess. In chapter 2, we saw a lot of equations where we just found, oh, x equals 5, or x equals 3/4, or something like that. But in this section, we're going to find that there are infinitely many solutions, which I guess we're actually a little familiar with, because remember in the section where we solved inequalities, like x is greater than 3, there were infinite number of solutions, so we were saying, you know, we can't really list them all, but what we can do is graph them, and we can write them in interval notation. So in this section, we're kind of in a similar boat. We have an infinite number of solutions. It wouldn't really be feasible to write them all out, you know. That would take forever, which is kind of silly. So what we do instead is we're just going to plot them on the Cartesian coordinate system. And it turns out that if you plot every single solution, all infinitely many, to one of these types of equations here, like the one in the box, it ends up being a line that goes on forever in both directions. So that's why we always graph lines, because we're just letting someone know this is a visual representation of all the solutions to this equation. Since there are infinitely many, I can't really tell you what they are, but I can draw a picture of them. That's really the best I can do. So that's the idea behind this section. I think when people learn how to graph lines, they kind of forget why they're doing it, and they just think, what kind of useless crap is this, you know? Excuse my French. But yeah, that's the idea. So in example 1 here, we have, we're just kind of trying to get the hang of it. We're not going to quite graph lines yet. We're just going to see what solutions look like. How can you even tell if an ordered pair is a solution or not? So in example 1, we're looking at that exact same equation that I wrote above, 3x minus 2y equals negative 6. And they want us to figure out if the following three ordered pairs are solutions. So I guess what I would imagine is, you're just going to, for example, if I focus on the first guy, 2, 6. 2 is the x-coordinate, 6 is the y-coordinate. So I would probably imagine I'm going to substitute those values into the equation to see if it's true or false. So that's the idea. We're going to test each of these three ordered pairs separately, one at a time. That's really all we're going to do, substitute the values. And if you get a true statement like 5 equals 5 or negative 2 equals negative 2, then it is a solution. But if you get a false statement like 5 equals 7 or 0 equals negative 5, that means it's a false statement. So let's test the first guy. We might as well look at 2, 6 first. And then later on, we'll test the next point, and on and on. But like we said, you just take the equation you're given. It was 3x minus 2y equals negative 6. And I'm going to replace x, like we said, with the x-coordinate of this point 2. And then we're going to replace the y-coordinate of this, or the y in this equation with the y-coordinate of the point 6. Alright, so 2 was x. I'm going to replace that where x was here. And 6 was y. So I want to put that where y was. And then I'll just simplify this as much as I can until I can see if it's true or false. So it looks like it's 3 times 2, that's 6, minus 2 times 6, that's 12. I'm going to see if that's equal to negative 6. Actually, that is true, right? 6 minus 12 is negative 6. So that means, yes, that point is a solution to this equation. Let's test the next one. We'll just keep doing the same exact thing. But the next point they gave us here was negative 4, 3. So I'm going to test that guy and see, do I get a true statement or a false statement when I substitute that in? So the equation, it was 3x minus 2y is negative 6, but this time I'm replacing x with negative 4 and y with 3. Let's see if we get a true statement or not. See, I put a negative 4 where x was and a 3 where y was and see what happens. See, we got 3 times negative 4, that's negative 12. Negative 2 times 3 is negative 6. I don't think that's going to happen, right? That's negative 12 minus 6, that's negative 18. I don't think negative 18 is equal to negative 6. No. Okay, that means that that point, negative 4, 3, was not a solution to that equation. Alright, we'll test the last one now. And we'll move on. We got the last point they gave us up here was 0, 3. Let's test that guy. And at this point, you're probably getting the hang of it, right? I'm just going to replace the x in this equation with the first number that I'm given here, 0. And I'm going to replace the y coordinate, or the y in this equation with the y coordinate 3. And we'll see if we get a true statement or a false statement. Some of these, though, like this point is, or this ordered pair is pretty simple, right? 0, 3. You might even be able to test it in your head, kind of just see how it looks. Let's see. So it looks like 3 times 0, that's 0. 2 times 3 is 6. 0 minus 6, that's negative 6. Oh, that's true. Okay. So it looks like the first and third points they gave us are solutions, but that middle one, that negative 4, 3, that was not a solution. And that's all they wanted in that one. Just kind of, they just want us to be able to first, before we even graph lines, make sure we even know how to tell if a point is on a line or not, or how to tell if a point is a solution or not. All right, let's try this other one. This second example, we're going to do the exact same thing, but we're given kind of a more complicated equation because it has a fraction in it, negative 2/5. So I'm not too excited about that, but, what are you going to do? I'm going to do the same thing. I might as well start with the first one they give me here, 0, 4. And I'm going to substitute that in for the x and the y. So the equation they gave me in this one, though, y equals negative 2/5 x plus 6. This one's a little trickier because the x and the y are kind of in different places on this equation. They're not in the same places as they were in example 1. So I got to be careful because when I'm given an ordered pair like 0, 4, the first coordinate is x and the second coordinate is y. But notice in the equation, y comes first and then x. So I better be careful which one I put where, It's not always the left number goes in the left spot and the right number goes in the right spot. It really depends on where x is and where y is. So I noticed y was 4, so that's going to go where y was there. And x was 0, so I'm going to put that where the x was here. And we'll see if that's true or false. So the left side, I just put it in parentheses because I think we discussed before that it's a good idea when you substitute values for a variable to put it in parentheses. It usually helps when there's a negative or something else, besides that number. But on the left side of this equation, I just had a 4, so there wasn't really a need to have parentheses. But now on the right side there, I have negative 2/5 times 0. You know what? I was thinking, let me put this 0 over 1 and go on, but now that I think about it, anything times 0 is 0. So negative 2/5 times 0 would be 0. So the right side, 0 plus 6, which is 6. And the last time I checked, 4 is not equal to 6. I guess that means that point 0, 4 is not a solution to this equation. That's kind of sad. Oh well, let's try the next point. We got 10, 2. I'm going to try that guy. So probably at this point you're getting the hang of it. You're just thinking, alright, so I know that the left number they give me is x, the right number is y. Doesn't really matter what the equation is that I'm given. I'm just going to replace x with the x coordinate, y with the y coordinate, simplify as much as I can, and see what happens. Is it true or false? All that stuff. Okay, so the x value was 10. but x is way over here, and the y value is 2. Alright, see what happens here. Simplify this guy. You know what I'm going to need to do on the right side? I'm trying to multiply -2/5 times 10. But I'm going to need to put that 10 over 1 if I want to see what happens with those guys. And I'm not too happy about this because I don't like fractions as much as whole numbers, but I can reduce this. Notice that 5 goes into 10 twice. So that fraction, those two fractions multiplied together, it actually just comes down to -2 times 2, which is -4. And they're both over 1. So it's 1 times 1 on the bottom, which is 1. And that's 2 equals... Let's see, and you know what? -4 over 1, that's just -4, right? -4 plus 6 is 2. So that is true. Ah, that means that was a good... 10-2 is a solution to that equation. Alright. Looking good. We got one more. Sorry, and I probably write larger than you guys do. I'm sorry. I'm running out of room, but if you want to write smaller than me, that's probably a good idea. Alright, last point they want us to plot, and then I think we're ready to move on. Let's try that guy. So I'm going to write that equation again. And maybe if you don't mind, I think now that we got the hang of it, I'm just going to leave blanks. It was y equals -2/5 times x plus 6. You know, now that I'm kind of familiar with this, in this point, my x-coordinate is -5. X goes here. And my y-coordinate is 3, because y goes there. So I'm just kind of copying the same equation as above, y equals, and replacing y with 3 and x with -5. Alright, let me see if I can simplify this. 3 on the left. On the right, if I want to multiply those, I'm going to put that 5 over 1. And you know what? Those reduce as well, right? 5 can go into 5 evenly. So all that's left there is -2 times, that would end up being a -1. So why am I putting negative? -2 times -1 is +2. Plus that 6 that was already there. 2 and 6 is 8. Okay, that's definitely not true. That is a no. Oh, I noticed on the last one I should have put yes, huh? Because the question they asked was, is this point a solution? And I said true. I guess that sounds it sounds okay, huh? But it's probably more correct to say, yes, it is a solution, rather than true, it's a solution. So I guess they want a yes or no answer, huh? I said true. Oh well, same thing. Alright, hopefully that sounds good. If it makes sense, you're ready to graph lines and have a good time and all that. Okay, let's see this next example here. Notice that they're giving us a Cartesian coordinate system, which is kind of exciting. So how about in example 3, what are they asking here? They're saying they want us to show that these 3 ordered pairs are solutions to this equation -3x plus 6y is -21. So I guess they're telling us that they are solutions. They just want us to verify it. So we're going to do the same thing we did earlier. Substitute those values in. Just make sure that it is a true statement. Just to be sure that they're right. And then once we do that, we're going to plot those points and find another solution. So that's interesting. It's good to know if you know a couple solutions to an equation, you can find another one by plotting them. And we'll see how to do that. But let's first do, the first thing they mention is try to see or verify that these guys are actually solutions. So I'm going to take that, let's see, the equation they give us, and then I'm going to leave an empty spot where x and y were, and replace those with the x-coordinate 7 and the y-coordinate y. Or sorry, the y-coordinate 0. X is 7, y is 0. Let's see if that's true. So that looks like -21 plus 0 is -21. Yes, that's true, right? -21 plus 0 is -21. Alright, so they were right. They said that was a solution, and I guess I believe them now. What about the next guy, though? I'm not so sure. I don't trust these people, Who are these people that are making up these points? Come on. Let's see if that guy's a solution. So I'll replace 5 in for x this time and -1 in for y. It should be a solution, right? Or else they were wrong. They said it was. I'm going to try to verify. Put a 5 where x was and a -1 where y was. Let's see. So first we have -3 times 5, that's -15. 6 times -1 is -6. And that is true, right? Negative 15 minus 6 is negative 21. Okay, so far, I guess I can trust these guys. We'll see, though. What about the last one? These sons of guns. The last one. Okay, they want us to test... Oh, it's a fraction? Or it's got a fraction in it? I'm not happy about that. Oh, well, what are you going to do? Alright, let's see. I'm going to replace those coordinates in for x and y. It was negative 3 times x plus 6 times y is negative 21. My x coordinate is 0 and my y coordinate is negative 7 halves. I'll replace x with 0 and y with negative 7 halves here. Ugh. Well, I kind of like the way the x coordinate is 0 is interacting. Negative 3 times 0 is 0. That's nice. Let me be careful here. I've got 6, and I'm trying to multiply it by a fraction, so I better put it over 1. Multiplied by, oops, negative 7 halves. Alright, I don't know why I put the negative in the numerator. It doesn't really matter, like we discussed before. But now that I see these guys, I want to reduce before I multiply. I can see this 2 goes into 6 3 times. So it ends up being the numerators 3 times negative 7, that's negative 21, over 1 times 1 is 1. But like we said before, anything over 1 is that thing. And that is true. Negative 21 is equal to negative 21. So I guess they were not lying about those 3 points being solutions. Alright, I guess I trust them. Alright, but that wasn't the end. Now they want us to plot those points. So let me see, I'm going to remind myself what those points were. 7, 0, 5, negative 1, 0, negative 7 halves. Alright, so 7, 0, we've been training for this in the last section. 7, 0's here, because you're looking for where's 7 on the x-axis and 0 on the y-axis. And 0 on the y-axis means I don't go up or down. I stay exactly on the x-axis. The next point, 5 is x, y is negative 1. 5 is here on the x-axis. Negative 1 is down here. So I need to go right 5, down 1 to get there. Alright, looks good. The last point, I'm not too happy about this one though. I've got 0, comma, negative 7 halves. I'm kind of wondering, how am I going to graph that? I think the best way to do that is change any improper fractions to mixed numbers. So that we have negative 7 halves. That's improper because the numerator is larger than the denominator. So I'm going to need to take that and divide. I'm going to divide that denominator into the numerator. 2 goes into 7 3 times at most, with 1 left over. So that means negative 7 halves is the same as 3 and 1 half. Well, negative. So that's probably a better way to write it. I'm going to rewrite this guy as 0, comma, negative 3 and a half. Or if you like decimals, you can say 0, comma, negative 3.5. That's fine too. That's a lot easier to find though. Okay, so the x-coordinate is 0. That means I don't go left or right. I'm staying directly at the origin. But then the y-coordinate is negative 3.5 or negative 3.5. I'm going to go down to that, somewhere right in the middle of negative 3 and negative 4. Past negative 3. So there it is. And notice, I didn't maybe plot these perfectly, but you notice those 3 points, they kind of line up, right? They kind of look like a line. So what I'm going to do is, since that's where we're trying to go in this section, is try to connect those and make a line with them. I'll try to make it as straight as I can. The best bet is to use like a straight edge, you know? A ruler or the edge of your book or the edge of your driver's license or something like that. Let's see, does that look straight? It's pretty good. And then just by convention, you just want to show people that this line goes on forever. So you're going to put arrows at either end just to indicate that this line goes on forever, upward and downward, or left and right. Alright, so we graphed it, and now they said they want us to plot those points and use them to find another ordered pair. So let's see, another ordered pair. Well, like we discussed above, every single point on this line is a solution. So all I have to do is figure out, other than those 3 points I plotted, which are here, here, and here, where is another point? I mean, is there a nice one that kind of intersects in a nice place? Let's see. So there's a lot of right answers for this part where they say, find another ordered pair. I mean, any other point on this line is correct. I'm just kind of trying to find one that might line up in a nice way. Looking at this guy. I mean, I'm just kind of grabbing a random one, but I kind of look at this point here. I don't know if you can see what I'm circling. That looks like a nice point, you know? It lines up, it looks like it lines up right on that grid, right on one of the lines. And it looks like it lines up with the x-axis at 9 and the y-axis at 1, I believe. You think that sounds good? I think that looks right, but you know, the thing is about these problems, I didn't use a straight edge. I just kind of tried to draw that line, or, you know, connect those dots and make the line as straight as I could. But what if I kind of made the line crooked and I had it go through the wrong point? I should probably check to be sure this guy's actually right. That's what we've been training our whole lives for. Or, okay, not our whole lives, but for the last, you know, section or two. I'm gonna check this guy to make sure he's correct, because I think looks like it's a solution by looking at the line, but I want to be sure. All I have to do is substitute those values back in the original equation. Remember, the equation was negative 3x plus 6y was negative 21. Let's see if I substitute those for x and y. Am I actually going to get a true statement or a false statement? If it's false, that meant I didn't draw this line very well. It looked like it went through that point, but it didn't really. Alright, let's see if that's true or not. That's negative 3 times 9, negative 27, plus 6 times 1 is 6. Is that negative 21? Yeah, it is, right? Yes, it is! Because negative 27 and 6 is negative 21. Yay, we did it! So just for situations like this, I would say, especially if you're graphing on a piece of paper and you have something, you know, a straight edge, like the book or something like that to guide you, I would definitely use that because it's going to help. Alright, sounds good, you guys. Hopefully that was all good stuff. Let's see if we can graph some lines. Now that we kind of know how it works, you know, we noticed as long as you know maybe 3 points on a line, then you're going to be able to graph it. Now they're going to kind of take the training wheels off in a way, and they're going to just give us an equation, like here in example 4. Say, here's an equation. We're not telling you any of the ordered pairs. You have to figure them out yourself, and then you're going to graph this line. But don't worry, we have a guideline here. This is how it's going to be done. Alright, so what does it say? To graph a linear equation like this one we're given, you're going to select a value for one coordinate and substitute to calculate the corresponding value of the other coordinate. So I've noticed that a lot of students, they do not like this. I think because usually in math there's only one right way to do it, you know? Like when we solved equations, you have to do this, and then you have to do this. But here, graphing lines, there's a lot of right ways to go. So they're saying, you're going to just choose a value for either x or y. And it doesn't matter, you can pick literally any number. But I think what you want to do is pick a number that's not so huge. So I like 0, because 0 makes things really nice. Or maybe 1 or negative 1, those kinds of numbers. But my favorite is 0. But you're free to choose whatever you want. You could pick x equals 1,000,000 if you want. It's just going to be kind of tough or more complicated. So that's my first step. I'm going to choose x equals 0. But you notice that it said to select a value. Okay, I picked 0 for one coordinate. So even though I let x equal 0, I actually could have let y equal 0. So you choose two things. You choose x or y, whichever one you want. And then you choose a number to let that be equal to. You have a lot of freedom. But I think if you like something simple, 0's good. Or 1. 1's good too. So we selected a value, and then as it says here, we're going to substitute that into the equation to calculate the other coordinate. So we kind of, in these situations, we have 1 degree of freedom. I can choose one of them, say x equals 0, or I could choose y equals 3, or whatever I want, but I can't choose the other coordinate. Once I say one coordinate is something, the other coordinate's going to be predetermined. So I can't say x equals 0 and y equals 5. No, once I let x equal 0, y is already determined for me. I just have to substitute the value that I chose. Since I chose x equals 0, I'm going to substitute that value into the equation for x. And whatever y comes out to be, that must be the corresponding y value. So what'll that be? If I put a 0 there, negative 4 times 0, that's 0, plus 5 is 5. So those two, the x value of 0 and the y value of 5 must go together. They make an ordered pair. So like it says there, once you find that value, you're going to form an ordered pair. Alright, so all that work I just did was just to find, I found 1 point. 0 was the x value, because that's what I chose. 5 was the y value, because that's, like I said, it was already predetermined once I chose x equals 0. Alright, so we've done that. Excuse me. And then step 2 says, we're going to repeat that process to find another ordered pair. But of course, I'm not going to use the same x value, because if I let x equal 0 again, y is going to be 5 again. And I just wasted a bunch of time trying to find the same point. So I'm going to let... And at this point, like we said before, you're able to let y equal something if you want. But maybe just because we're just trying this, just starting out, I'm going to let x equal something again. Let x equal... And again, I would... Just to simplify it for yourself, keep x close to 0. You know, maybe try 1. I don't know, because 1 is a nice number. You won't get in too much trouble with 1 or 0. But you're going to do the same thing. I'm going to replace the x with 0 in that original equation they gave me, y equals negative 4x plus 5. But this time x equals 1. So I'm replacing x with 1 there. And then simplifying. Y equals, let's see, that'd be negative 4 times 1 is negative 4 plus 5. That would be y equals 1. Okay. We have another ordered pair. I got the x value I substituted in was 1, and the y value I got was 1. Okay. Sounds good. And then, let's see. We have 2 points, but notice in the directions they say, a third ordered pair should be found to use as a check. So the thing is, you really, just so you know, you technically only need 2 points to graph a line. So let's say I plotted the points that I found so far. 0, 5. Okay, that's gonna be up here. Because 0, I don't go left or right, but 5, I go up 5. The other point I found was 1, 1. Where's that guy? Here. 1 on the x-axis, 1 on the y-axis. You can imagine, what if I connect those 2 dots? Well, then I know exactly what the line looks like, right? There's no need to find a third point. But they encourage you, and I would probably encourage you to find a third point, because what if you made a mistake on one of those 2 points that I found, you know? You substituted wrong, or you added wrong, or something. You would never know you did something wrong, but if you find a third point, then I think that's a good idea. Because then, if you find a third point and the 3 points don't line up in a line, then you know you made a mistake. So it's good to find a third one to check your answer. I'm going to try one more. Let's try to let... I don't know. It's hard to say. It's up to you. It's anything you want. But I'm kind of boring, so I'm going to let x equal... I don't know. Negative 1? Yeah, you have the freedom. You can choose x equals 5. You can choose x equals 20. Negative 37. Whatever kind of weird number you want. But it's in your best interest to keep it kind of small and a nice number. Okay, so again, I'm going to take the equation. It was y equals negative 4x plus 5. But this time I'm replacing x with negative 1. I'm going to see what I get there. Let's see. Negative 4 times negative 1 is positive 4. Plus 5 is 9. Aha! So there's another point. I substituted negative 1 for x, and I got a 9 for y. So that was a third point. And if these 3 points line up perfectly in one line, then I know I've done everything right. But if maybe these 3 points, like 2 of them look like they form a line, and the third one's kind of out in left field, then you know you made a mistake. So you can always catch your mistake by finding 3 points. But like I said, 2 is all that's necessary. So maybe once you get the hang of these and you feel really good about them, all you really need is 2 points. But 3 is good for when you're first starting out and you're afraid you're going to make a mistake. Alright, let's plot that third point. Negative 1 for x. So you're going to go left to negative 1, and then up to 9 on the y-axis. That would be here. I think those line up pretty well, right? That looks like a line to me. Alright, let's just connect those 3 dots as best we can. And I wish I had a straight edge, but, you know, what are you going to do? You do your best. There we go. Oh, man, that looks bad. Okay, the more I draw on it, the worse it gets. I better stop while I'm ahead. Alright, that's a good-looking line right there, you guys. And that's all they wanted, just... Now remember, that seems pointless, sort of. I think a lot of people think that. What the heck was the point of drawing that line? But it's just, this is a visual representation of all the solutions. There are infinitely many solutions to that equation that we were given. And I just represented them all in that graph. Because I can't list them all. It's not physically possible to list all the solutions. Alright, let's try the next one here. We got, it looks like 4x minus 2y is 16. So I'm going to do the same thing. I'm going to try to just choose 3 different x values, plug them in, see what the y values are, plot those points, bada bing, bada boom. And I didn't mention this in the last example because there was already so much going on. I didn't want to confuse everything, but a nice way to kind of gather your thoughts, I know, is to make a little table. So I'm going to make 2 columns, one for x and one for y, and then 3 rows below. And that way I can keep my thoughts kind of gathered. And then the first thing I'm going to do is think about what x values do I want to substitute in there. Well, you know, in the last one, what really worked out was 0. 0 is my favorite number because replacing x with 0 or y with 0, oh my gosh, it's so much nicer. And then, I don't know, it's up to you guys, but maybe you want to mix it up. I know it said in the directions, you can let x equal something or you can let y equal something. So maybe in the next one, I'm going to let y equal 0 and see what happens. I mean, I used the same value, which is a no-no, but that's only if you try to use the same value for the same variable. And the first time I'm going to let x equal 0, and then the second time I'm going to let y equal 0. That's going to result in 2 different points. And then the third point, I mean, I can choose x or y to be something. I guess I can't choose 0 because I've already done that. Maybe I'll let x equal 1 or something. I don't know. Why not? We'll see how that goes. Okay. So it's nice to have those there to gather your thoughts, and then I'll kind of do the scratch work over here. The first value that I chose was I let x equal 0. Once I do that, I'm going to see what happens. What would that do to y? So let's see, I'm going to rewrite my equation. It was 4x minus 2y equals 16. But since I let x equal 0, I'm going to have to replace x with 0, leaving y as is, and try to solve for y. So okay, put a 0 where x was, and we'll try to solve for y. 4 times 0 is 0, minus 2y is 16. But 0 minus 2y, I mean, that's just negative 2y. 0 doesn't really need to be there, which is nice, so that's why I like to choose x equals 0 or y equals 0. Okay, now I can solve for y pretty easily by dividing by negative 2. Not bad. Alright, so we've solved for y. Y must be negative 8. Huh. Interesting. So that means that the corresponding y value that goes with the x value of 0 is negative 8. So I'm going to just throw that in the table. Yeah, it's kind of nice to have a table so you have all your thoughts in one place. You don't have a bunch of scratch work here and there and you got to go looking for all your points. Where are my ordered pairs? I don't remember where I put them. Okay, let's try the next one. The next value that I put in that table was, I put a 0, but this time it was for y. So this time I'm going to let y equal 0. And see what happens with that equation. The equation was 4x minus 2y is 16. And I'm replacing y with 0 this time, not x. This time I'm leaving x as is. And where y was, I'm going to replace it with 0. Okay. We'll try to simplify this guy, and then we'll try to solve for x. So let's see, 4x, and then, of course, 2 times 0 is 0. So you know what? I could write plus 0 or minus 0. That's not going to do anything. I'm just going to... I know that guy disappears. He's 0. He's gone. So the equation just comes down to 4x equals 16. If I solve by dividing by 4, I find that x equals 4. Okay. So that means I can start filling in the table more. For that point where I let y equal 0, the x value is 4. Alright, make sure it lines up because the left column is my x column. So I filled in 4 for x. Alright, there's one more point that we wanted to find, and I think that'll do it. So the last one, in the table we let x equal 1. But you could have just as easily let y equal 1. I could have put 1 for y and then solve for x. Just kind of, I don't know why I picked x, just, I don't know, for fun. Alright, I'm going to take the equation 4x minus 2y equals 16 and replace the x with 1 this time. It's not going to be as nice as when we replaced it with 0. That was too good. But it'll still work out. Alright, let's see, I'm going to put a 1 where the x was, and now solve for y. So I've got 4 times 1, that's 4, minus 2y equals 16. Now if I want to solve for y, I'm going to have to move the 4 over, so I'll subtract it here. And that'll give me negative 2y all by itself. How about over here? 16 minus 4 would be 12, I believe. Alright, thankfully, if I solve this, negative 2 divides into positive 12 an even number of times, negative 6. Whew, okay. So that means that the very last coordinate that I was trying to find is negative 6. Whew, alright, we found 3 points. So you can read all your ordered pairs from left to right. You notice the first row below x and y was 0 for x and negative 8 for y. There's one ordered pair. The next row had 4 for x and 0 for y. There's another ordered pair. The last ordered pair I just found, x was 1, because that's what I let it equal. Then I found that y was negative 6. Alright, so now I'm going to plot those 3 points, make sure they line up all in a straight line. If all 3 of them are in the same line, I know I've done this right. But if one of them's off in somewhere else, then I know I've done something wrong and I better check my work. So might as well start with the first one. 0, negative 8. 0 means I don't go left or right, because that's the x-coordinate. But negative 8 means I go down 8, so he must be here. And then the next point, 4 is the x-coordinate, that means I go right 4. And 0 is the y-coordinate, so I don't go up or down, I just stay right on the x-axis. Alright, the last point, 1 is the x value, negative 6 is the y value. I'm going to go right to 1, and then down to negative 6. It would be about right here. And I think those look like they all line up, right? Okay. I must have done something right. Let's connect the dots, and we'll call it a day for that one. That doesn't look like a line. You know, you gotta pretend like I can draw a straight line here. Pretend this is a straight line, okay, guys? Alright, looks good. Sounds good. I know this seems really tedious. We'll have kind of faster ways to do it, but this is a good way to just kind of get the hang of it, you know? Alright, let's see about this next one. So this next one is just more of the same, more practice. But the very last example is kind of an interesting one where it's how to use this in real life. You know, what use would this be in real life? Okay. So the last one here, or example 6 we got, they want us to graph this line y equals negative 1/3 x plus 2. Alright, and notice that this one, I think this is the first one we've seen in this section, I believe, where y was by itself. It's y equals blah blah blah. So it's, you know, it's a good thing to keep in mind, since we're making our own table, you know, x, y, we get to choose whatever we want for x or y, whichever we like. When y is by itself, like we have in this equation, it's probably easiest to choose values of x. So I'm just going to let x equal 3 different things. I'm not going to choose something for y because it would be too complicated. So that's a good idea. When y is isolated, like we have, oops, isolated, choose x values instead. So you notice in that last example we did, where is that guy? Where did he start out? 4x minus 2y is 16. That one, it didn't have x or y by itself. They were both kind of mixed up on the same side of the equation. I don't know if it was really easier to get x, you know, or to let x equal things or y equal things. But if you have an equation where one variable is all by itself, oops, sorry, then it's going to be easier to let the variable that's not by itself equal things. And we'll kind of see why. How about, so we're going to let x equal a few things. And in this one, you know what else? You want to be really strategic here because, you notice whatever I let x equal, it's going to have to be multiplied by negative 1/3. So I want to be strategic, and I'm going to think, since I have the freedom to let x equal whatever I want it to, I'm going to even write this down. Let x be a number. I want it to be a number so that when you multiply it by negative 1/3, I'd rather get a whole number from that. So what kind of numbers can you multiply by a third and get a whole number? Well, they're numbers that are divisible by 3, because a third of something that's divisible by 3 will be a nice whole number. That is, what you could say, is divisible by 3 or is a multiple of 3. Of 3. For example, like 3, 6, 9. Those are the numbers that are going to look, or that are going to interact with 1/3 really nicely. Or negatives too. Negative 3, negative 6, stuff like that. So you could actually pick whatever you want, but I just know that if I pick something that's not nice, like a multiple of 3, I'm not going to get a very nice answer. So let me see. I'm going to choose... Well, my favorite, like I said before, is 0. Because 0 interacts with any number really nicely. So imagine if you put a 0 there. 0 times negative a third, that's 0. So the whole fraction disappears and you're left with something nice. So 0 you won't have to worry about, but the next coordinate I choose for x, I'm going to try to choose something nice like 3. We talked about 3. Because I know that 3 times a third is going to be really nice. And I need one more. You could choose 6 or 9. I'm going to choose negative 3. I don't know, I think staying sort of close to 0 is good. If you choose a large number, your y value might be too large and it might be far off the graph or something. Alright, so I think those are good ones. I'm going to choose, start with 0. Let x equal 0. And then see what happens to y. So y, from this equation, it's negative a third x plus 2. But remember that you're replacing x, so x is 0. Let me see what happens there. Like we kind of discussed, 0 times a third is 0. 0 plus 2 is 2. So that must mean that the corresponding y value that goes with the x value of 0 must be 2. Alright, that wasn't too bad, huh? Maybe we'll try the next guy. Let x equal... You know, maybe just... You shouldn't write this down, but I'm just going to show you why choosing an x value other than 3 would be bad. Like, you know, before I was saying, I like x equals 1 because it's a nice small number, but imagine I put a 1 in for x right now. I don't want to do that, I'm just showing you why it's not going to be pretty. What if I put a 1 where x was? Here, let's see. 1. What's negative a third times 1? You put the 1 over 1, you have to multiply across because nothing reduces. Negative 1/3 plus 2. Oh, that's going to be ugly, right? I mean, you have to find a common denominator, put the 2 over 1, multiply it. No, I don't want to do that. If I can help that, I'm not going to want to do that. So that's why I choose something that's, you know, divisible by 3, because that way it'll reduce with that fraction and make something nice. So, okay, I chose 3, right? I'm going to substitute that guy in there. So it was y equals negative 1/3 times x plus 2. But I put a third, or 3 where x was. And so in order to multiply those guys, I'm going to put that 3 over 1. So I have a negative 1/3 times 3 over 1. And you notice, we chose it strategically, those 3's cancel. All you're left with is negative 1 times 1, which is negative 1. So that just comes down to the two fractions multiplied together makes negative 1. That plus 2 is just positive 1. That's not so bad. Even though there was an ugly fraction, it didn't really matter. So that means the x-coordinate of 3 goes with the y-coordinate of 1. So we went ahead and replaced that guy. Alright, let's look at the last one now. We're going to let x equal negative 3 and replace that. Y equals... supposed to be negative 1/3 times x plus 2, because that's the equation we were given. But I'm replacing x with negative 3 this time. And I think it's going to work similarly. I'm going to do like we did in that last part and put the negative 3 over 1. So it's negative 1/3 times negative 3 over 1. And whatever that is, I'll add 2 to it. But you notice those 3's cancel as well. The only difference here is this time we're left with a negative 1 times a negative 1, which is a positive 1. And then we're adding 2. So we'll get 3. Okay, so that must mean that the last coordinate is 3. I think that looks good. Alright, so our 3 points are... Sorry, I'm kind of running out of room here. 0, 2, because that was the first row, x comma y. The second row, 3 comma 1, x comma y. The last row, we just found negative 3 comma 3. Alright, so now we'll see if we got the right points. In these types of problems, it's easy to make a mistake because the fraction is easy to mess up. But if those 3 points line up in one nice line, then I know I did it right. So the first point, 0, 2, that would be here. 3, 1 would be here. Negative 3, 3 would be here. I think those do line up in a line. Hey, nice. Let me try to, hello. Try to connect those guys. That would be wee. Wee. Okay, that doesn't look like a straight line, but you know, you gotta use your imagination there. Looks good. I know it seems like a lot of work just for a measly little, I don't know, not a great result. But it is useful later. And like I said, we'll see other methods, and I think you might even like the methods that we'll see that are probably a little faster for graphing a line. It's just good to practice these ones. Okay, last example. This says, it gives us kind of an equation of a line, sort of. You notice it says up here in the second line, v equals -3/4 t plus 6. So it looks strange because they're not giving us an x and a y coordinate. They're giving us v and t. But just kind of pretend like it's x and y. It's just different letters, but we're really thinking of it as the same thing. But in this problem, they're using v and t because this is a real-life situation, and v and t represent something in real life. All right, this example, they say the value v, okay, that must mean that this v in this equation represents the value of a shopkeeper's inventory software program in hundreds of dollars. So whatever your value of v is, that represents how many hundreds of dollars this software program is worth. It's given by this equation, and then they say where t is the number of years since the shopkeeper bought the program. So basically they're saying t is the age of this program. How old is it? They want us to graph this equation and use the graph to estimate what the program is worth 4 years after it was purchased. All right. So it seems kind of silly, but we're going to do like we did in the last one, but we got to kind of, instead of thinking of x and y, we got to think of it as t and v. So maybe over here in this coordinate system, I have an x-axis and a y-axis. I'm going to cross that out, make it t and v instead. And you know, probably at this point I'm thinking, wait, how do you know which one's t, which one's v? I would say go in alphabetical order. Alphabetical order. You know how we said the x-axis, since x comes first in the alphabet, that's the vertical or the horizontal axis. And then the y-axis comes second because that comes second in the what's it called? The alphabet. Same thing with v and t. T comes first before v in the alphabet, right? First in the alphabet. And v and y, they come second in the alphabet. So that's kind of how you know which one corresponds to which one. You know, is v x or is t x? And which one's y? Just say, all right, x comes first in the alphabet. He corresponds to whichever of these variables, t or v, comes first in the alphabet. So now I must think that t is x and v is y. So now when I make my little table of values, instead of using x and y, I'm going to use t and v. I know it seems strange. Now we just got used to x and y, and now they're kind of flipping the script on us. But oh well. We know it means the same thing. Okay. And you know, this example, notice that this equation has v by itself. V equals something. So like in the last problem, remember how we said we had y by itself. So we said it'll be easiest to substitute values of x in. I think this will be similar. I'm going to substitute values of t in. Values of t, because it'll just be easier to figure out what the other guy is. Alright, but also, I want to be strategic here, like we did in the last one, because whatever I substitute for t, you notice in the equation it's going to be multiplied by a fraction, 3/4. And I would like to not have fractions in my answer, so I want to make sure that whatever I put in for t, I want it to multiply by 3/4 and become a fraction. That must mean I think I want t to be a multiple of 4, because I'd like to see that 4 divide into whatever t is evenly. Well, first of all, 0 always works, because 0 times 3/4 is 0. It won't be a problem. But maybe the next one I'll let t equal 4, because again, I know 4 is divisible by 4. And then maybe we'll try -4. Or you could have done 8, because 8 is divisible by 4, or 12, or 16, But I just kind of like to stay close to 0, because I don't want to have values that are off this grid, you know? A lot of times if you substitute a large value in, like t equals 12, the v value might be really large, and it might not even be on this grid anymore. So you kind of want to keep it sort of close to 0 if you can. Okay, let's see if we can figure these values out for v. The very first one we substituted in, I'm going to let t equal 0 and see what happens. Well, v is equal to -3/4 times t plus 6, just kind of copying the equation we were given. But in this one, we're replacing t with 0 because that was the first value that I chose. Let's see how that goes. Well, negative 3/4 times 0 is 0. That's nice. Plus 6 is 6. Alright, so that must be the v coordinate for this point. 6. Alright, there's one ordered pair, 0, 6. Not too terrible. Okay, let's try the next one. The next value that I let t equal was 4. We'll see how that looks in here. What we got? Same equation, v equals negative 3/4 times t plus 6. But this time my value of t I replaced with 4. Okay, and unfortunately 3/4 times 4 isn't pretty, so I'm going to put the 4 over 1 so I can have a hope of multiplying. Let me rewrite this again. It's negative 3/4 times 4 over 1, and then I'll add 6. So for sure those 4's cancel, which is kind of by design, right? That's why I chose 4, because I knew I'd get a whole number here. So the only thing I get left from those fractions, negative 3 over 1, which is negative 3, plus 6. So it's negative 3 plus 6, which is 3. Looks good. So that must be the y, or I was going to say y coordinate, the v coordinate for the second value, or the second ordered pair. Okay, last one. Now we're going to let t equal negative 4, and then we'll be ready to graph, and I think we'll be not too far from finishing the section. Alright, let's see. So the equation was v equals negative 3/4 times t plus 6. But I want t to be negative 4 this time. Negative 4 is going to go in there, and just like in the last part, I have to put the negative 4 over 1 if I want to have any hope of simplifying this. Negative 3/4 times negative 4 over 1. Well, the 4's cancel, just like in the last part, but I got to be careful because it's still a negative times a negative. So it's a positive 3 plus 6 that's left over. So it looks like 9. V is 9. That must be the other coordinate. Last one. Whew. Okay, so we got 3 points. I'm going to write them down real quick here. Our ordered pairs. The very first row that we found, it was 0. That's what we chose. And then 6 popped out for the other variable. The other one, we chose 4 and 3 popped out. Then the last one, we chose negative 4 and 9 popped out. So let me see if I can plot those points and see if I don't get a nice line. So the first point, 0, 6, would be up here. The next point, 4, 3, would be here. And then what? Negative 4, 9 would be... Where are we? About here. Alright, those 3 look like they line up perfectly, huh? In a nice line. Let me try to connect those guys. I should be using a straight edge, but it's kind of hard on a computer here. Okay. Looks good. So that's what they wanted, but I think they want us to answer one more question. But all we have to do is look at our graph. So what are they saying? Oh, no. They want us to estimate what the program is worth 4 years after it was purchased. So I guess the question is, 4 is the number of years. Are we looking for when is t equal to 4 or when is v equal to 4? Well, remember t is time. So t equals 4 years is what we're looking for. So when is t equal to 4 years? That's right here, right? Because you're looking at the t-axis. So they're really asking where on the t-axis is t equal to 4. And then they want you to line that up with a line and say, alright, there's a point. Where does that line up with the v-axis? Looks like v equals 3. And then I gotta remember, what did v equal 3 even mean again? I already forgot. V, okay, what did they say in the problem? V, at the very beginning it says the value V of the inventory program in hundreds of dollars. Okay, so when we say in the end V equals 3, that means $300. Okay, so since this is a word problem, I should probably say something at the end. I'm sorry, it's kind of running out of room here. But the end result would be, what do we have? I'm going to write it at the bottom. After 4 years, because that's what t was equal to. T equals 4 is what they told us. The software program is worth, we found that it was worth v equals 3. But remember they said v is always in hundreds of dollars. So it's really worth $300. Alright, that was a tough one, but it does kind of show, I guess, where this is used in real life or something. Why would someone care? I guess it's if you know how much something's worth for a couple years and you want to project how much it's worth later or how much it was worth in the past, you can always project it by graphing a line and trying to line things up. So anyway, hopefully that all made sense. I know this was a long section, but since it's just the very beginning and an intro to graphing lines, I think that's why it took so long. The next couple sections should be shorter and more clear-cut, so thanks for sticking with it, and I'll see you in the next section. Enjoy. Have a good day. Bye.